Welcome to The Explainer. Today, we're going to dig into the hidden potential of one of the most common agricultural byproducts on the planet. This is the story of how a simple waste material is being used to create super strong concrete. I mean, that's a pretty wild question, right? It sounds almost too good to be true. But as we're about to find out, the answer is literally locked away in the ashes of our food supply, and it could totally change how we think about building our world. Okay, so concrete. It's the foundation of our modern civilization. It is everywhere you look. And for decades, engineers have been trying to make it stronger, more durable, just better. But the next big leap forward? Well, it's not coming from some high-tech lab. So let's meet the hero of our story. It's not some crazy new polymer or a rare element from deep in the earth. Nope. It's called rice husk ash. That's right. When rice gets processed, that tough outer shell, the husk, gets stripped off. A lot of the time, that husk is just burned for energy, and what's left is this incredibly fine ash. For years, everybody just thought it was junk, but it turns out this ash is packed with something called amorphous silica, and that is the key to its hidden talent. Now, to really get its power, you need to understand this term, pozzolanic activity. Think of it like a master builder that hates waste. See, when cement mixes with water, it creates this strong glue that holds concrete together, but it also makes a useless leftover product. A pozzolanic material, like our rice husk ash, swoops right in, grabs that waste, and chemically transforms it into more of the good stuff, more of that strength-giving glue. It's an efficiency superpower. So what does this pozzolanic superpower actually do when you put it to the test? Well, the source material we're digging into today lays out 4 incredible data-backed benefits. Let's break them down one by one. First up, and this is the big one, is compressive strength. This is all about how much crushing force a material can take before it just gives up. Think about the immense weight of a skyscraper pressing down on its foundations. That is compressive strength in action. So, how much of a boost are we talking about here with RHA? Get this, a staggering 51%. And you can see exactly what that looks like right here. In a study on ultra-high-performance concrete, just swapping out 30% of the cement with rice husk ash led to that 51% jump in strength. I mean, look at it. The bar on the right, the one with RHA, just towers over the standard mix. That's not a small tweak, folks. That is a game-changing leap in performance. But hey, strength isn't only about resisting getting crushed. The second superpower is flexural strength. If compressive strength is about taking a punch, flexural strength is about being able to bend without breaking. This is absolutely critical for things like beams in a bridge, or maybe the balcony on your apartment. And again, RHA delivers a serious boost. But check out the detail here. If you just use the ash as it is, you get a pretty good 4 to 16% increase. But if you simply grind the ash into even finer particles, boom, you jump up to a 15 to 21% increase. It just goes to show that the physical form of the ash matters just as much as its chemistry. All right, on to superpower number 3, splitting tensile strength. This is the material's ability to resist forces that are trying to pull it apart. You might think of concrete as always being pushed on, but its ability to handle tension is totally crucial for its overall integrity. Now, what's really interesting here is that this isn't a case of more is always better. The research shows there's a real sweet spot. For tensile strength, you get the best results when about 15% of the cement is replaced with RHA. So this is all about precision engineering, not just dumping more stuff in the mix. Okay, our fourth and final superpower is a little more technical, but stick with me because it's really important. It's called the modulus of elasticity. And all that really means is it's a measure of the material's stiffness, how well it resists being bent out of shape when a force is applied. And this is where things get really interesting. RHA kind of has a dual personality here. On one hand, its superfine particles act as a filler, plugging up tiny little holes in the concrete. This makes it denser and stiffer, which increases the modulus. But if you add too much RHA, the silica itself can be a bit more compressible, which can sometimes decrease it. It's all about finding that perfect, delicate balance. So we've seen the what, right? The 4 incredible benefits that basically turn regular concrete into something, well, super. But that just begs the bigger question, how? I mean, how can something as simple as leftover ash from rice have such a huge impact? So let's get to the science. The real secret, as we've already hinted, is that beautifully elegant chemical dance, the pozzolanic reaction. And the process itself is just brilliant. Okay, step 1, regular cement and water mixed together. They make the binding gel that gives concrete its strength, but they also leave behind a useless waste product. Step 2, the superreactive silica from our rice husk ash sees that waste and goes right for it. Step 3, it triggers a chemical reaction that transforms that waste into even more of the good, strength-giving binding gel. And the final result, step 4, is a concrete with a way denser, more refined internal structure. And that is where all that extra strength comes from. So when you put this all together, what does it all mean? Well, it's pretty clear that rice husk ash isn't just a simple filler. It's an active ingredient that fundamentally redesigns concrete from the inside out. So let's just recap the big takeaways here. RHA works its magic because it creates a much denser microstructure. And that physical change leads directly to those massive improvements in compressive, flexural, and tensile strength. And remember, the key isn't to completely replace cement, but to perfect the mix. The magic really happens at those optimal levels, usually somewhere between 10 and 30%. You know, this single sentence from our source material just perfectly captures the whole story. It's those two things working together, the chemical pozzolanic reaction and the physical microfilling of the tiny gaps that create a superior, high-performance material from something we used to just throw away. And that kind of leaves us with a really fascinating final thought, doesn't it? If this incredible potential was hiding inside something as common as rice husks, what other everyday waste materials out there hold the secrets to building a stronger, smarter, and more sustainable future? What other superpowers are just sitting there, waiting to be discovered in plain sight?